Hello, and welcome to Lecture 12, where we're going to discuss work and kinetic energy, in other words, the first sections in Chapter 5, covering the work and energy topics. All right, so let's get into some key terms. First of all, maybe covering the terms that are in the title of this lecture. Okay, so let's take a look. Work, kinetic energy, and so on. All right, so what do we have? Well, work, zoom in a bit on this, is a new quantity, all right, of force times displacement. That's all it is. It's just force multiplied by displacement. All right? It is equal to the component of a force parallel to a displacement vector. So you look at the force vector and the displacement vector, and you look at the component of the force that's parallel to the displacement, multiply that component by the full displacement, and you've got yourself the quantity called work. All right? And the name kind of says it all. It's work. It's actual mechanical action, right? It's doing things, okay? The work quantity is related to individual forces, and net work, which is a term we'll use a lot, is related to the sum of work values. And notice my wording there. Well, the reason I say values is because work is a scalar, okay? So it has units of Newton meters or joules, all right? Or I should say really J, because I haven't defined it as a joule yet, but spoiler, J stands for joule, okay? But Newton meter makes sense because it's force multiplied by a distance, okay? So, what is kinetic energy? All right. Well, you see this arrow going down below. There's the formula. But what's the term? Okay. Well, it's the energy of motion. It is energy is a quantity, right? Because what the heck is energy? That either can do work or is created by work. And kinetic energy is one form of energy. We'll talk about other forms of energy, but kinetic is the first one we're discussing. But see that relationship? See how we defined work first because it related to force, something we already knew? And now we're defining energy, and defining energy based on the definition of work. That way we're not really kind of jumping off a cliff in terms of new ideas here. We're building on previous ones. And like work, kinetic energy is a scalar with units J. All right, and what is J? It's joules. All right, so the joule, Joule, is a derived unit of work and energy. Okay, so it's the unit of both work and energy. Although sometimes you'll see that sometimes work is referred to as Newton meters instead of joules, but it doesn't matter. I certainly prefer referring to work in units of joules, so it has the same units as energy, and we're just being consistent. Okay, so a joule is represented by J, which is equal to a Newton meter, which in terms of base units is equal to the kilogram meter squared per second squared. And in terms of dimensions, it's mass times length squared times time to the negative 2 power. Okay? All right, net work. I mentioned it up above, right? I said that when you sum up work, so you get something called net work. It's the sum of work values, all right? Each force does work, so the sum of work is net work. So since work is a scalar, the sum is arithmetic. No components. It's not like a vector sum. We simply just sum up the values, which makes it fundamentally easier, a lot easier to work with than forces, certainly, okay, where we had to be careful to sum up the values, or even relative velocity, where we had to think about components. Right? We had some pretty complicated vector considerations, splitting everything in the right triangles. We don't have to do that with energy at all. This is all about scalars, okay? All right. And what is the work energy principle? Well, it's a fundamental relationship between work and motion, okay? And it really is based on the definitions that we presented before, the way that kinetic energy is defined as energy that is capable of doing work or is made by work, right? Likewise here, okay? So the work energy principle states that if net work is greater than 0, then kinetic energy must change. So if the sum of all your work values, and all those individual work values are individual force times the displacement, times the angle between the displacement, between the vectors really, the displacement and the force, okay? But I'll repeat that in just a moment. But if you sum up all those individual work values, you get the net work. And then you ask yourself, is that net work 0? Well, then there shouldn't be a change in velocity. But if that net work is not 0, then there must be a change in velocity. That's what the work energy principle tells us, okay? And here it is, right? I'm pointing an arrow to it. It simply says net work, so work with the subscript of net, is equal to delta K. And K is, remember, kinetic energy, okay? And I'll reiterate the form of the equations in a minute. But what's interesting is we've actually seen this before. So the work energy principle is really another way of saying that non-zero net force creates acceleration. So it's really a restatement of Newton's second law. Why would we even do that? Well, because what's the whole purpose of energy? Well, it won't become immediately clear until later in the chapter. But I'll tell you now, it's just a bookkeeping thing. It's just a way of solving problems in an easier way. because the way energy is conserved, because the way we can make these quick arithmetic sums without worrying about vectors, it just makes our life easier in certain situations. And it even allows us to solve problems that we couldn't easily solve with forces. Okay? But lots of times it's redundant. Okay? So it's something we could have done with forces and kinematics. But with energy, we might be able to do it faster. All right? You know, one thing we'll see though, and I definitely will be making a big deal about this, is all this energy bookkeeping, this easier way to solve certain problems does have its limitations, which you might expect, right? Because otherwise maybe we would just have started with energy a few chapters ago. Okay? So forces, fundamental, right? That's everything we can do with forces. That's fundamental physics. Energy is not fundamental physics. Energy is just a method of solving, a method of doing things. That's it. Okay? It's not actually new physics. All right, but hey, let's solve some problems, okay? But first, let's look at these key formulas, all right? So K stands for kinetic energy, okay? Sometimes it's KE as well, all right? But I tend to use K in my notes. I know your textbook actually, this version of it tends to use KE. And same thing, all right? It's equal to 1/2. This is just a constant, comes out of calculus, but we don't care really where it comes from here. It's just 1/2 times m for mass and then velocity squared, okay? So that's kinetic energy, 1/2 mv squared, okay? Work, represented by uppercase W, all right, is force times displacement, which is, here we're calling it D, but really before we probably would have called that delta X or delta Y, but here we're calling it D just by convention. And then cosine of phi, well, what is phi? Well, phi is the angle between F and D, right? So if I have a force vector like this and I have a displacement vector like this, then where the two tails touch, we look at that angle and that's phi, okay? So we see cosine, what does that tell us? It tells us if the two vectors are parallel, then it's cosine of 0, which is positive 1, right? So if phi equals 0, then cosine of phi equals positive 1. On the other hand, if phi equals 180 degrees, so if they're anti-parallel, then cosine of phi equals negative 1, okay? Before it was positive 1. I may have misspoken and said negative 1, so let me rewrite that again. So cosine of 0 degrees is positive 1. Okay? Now, what about if it's like 90 degrees, right? Well, cosine of 90 degrees is 0. Okay? So those are the kind of the big cases. Perpendicular, no work at all. And that would be perpendicular between force and displacement. Anti-parallels, pointing the opposite way, negative work. Because yes, work is a scalar, but it can be negative. Okay? Sign is not direction. Okay? And furthermore, SIGN, by the way, not like sign, like a, you know. But anyway, and then if it's parallel, then it's just multiplying the two together, right? It's just cosine of, the cosine just becomes 1. Okay, here is the work kinetic energy theorem, all right? All it's saying is that net work is equal to change in kinetic energy, and if we expand out change in kinetic energy, it's 1/2 mv final squared minus 1/2 mv initial squared, okay? So it's, because this is just k final, right? And then this is just k initial, and then we're just subtracting k initial from k final, okay? It's how much, positive kinetic energy change there is, or negative. You can have a negative kinetic energy change too. You can lose kinetic energy, okay? Which means your net work's got to be negative too, all right? Now, what's interesting is we can actually rewrite this expression, all right? Changing kinetic energy, as I said. So we can rewrite it, and I'm going to do a substitution. I'm going to replace V final with one of the kinematic equations, all right? You probably recognize this kinematic equation. It's the V final squared equals V initial squared plus 2a times delta x, but here D is just delta x, right? And look what that does, right? That cancels out the V initial squared term, and then we find that the net work is just mad, okay? It's just mass times acceleration times displacement. Pretty cool, right? All right, okay, so let's jump into some problems. All right, so we got a few types of problems. Simple problems that involve work, 0 acceleration, and only forces parallel or perpendicular displacement. So kind of simple in terms of angles, okay? Basically, it's always going to be cosine of 0 or cosine of 180. Then we have problems that involve work, constant non-zero acceleration, okay? So in other words, the net work is not going to be 0. In type 1, the net work is 0. And if that isn't immediately apparent, that's fine. That's the whole kind of purpose of this, to get practice with it and see those connections. So anyway, constant non-zero acceleration and only forces parallel or perpendicular to displacement. Type 3, fairly complex problems that involve work, 0 acceleration, and forces at various angles, okay? So did I said everything is it going to be all scalars? So what's the whole business about angles? Well, okay, it's true that the the work kinetic energy theorem is fundamentally a scalar equation. So once we get there, we're easy. We don't have to worry about components. But sometimes when we're setting things up and we're worrying about that, the force times displacement times cosine of an angle, well, the angle is right there, right? So the way I always think about it is if you're doing problems that involve work, you're stuck with angles, potentially. Okay, but once you move over to energy, then you finally left the angles behind. Work really represents this bridge from force diagrams to dealing with energy. Sometimes it's necessary. Obviously, we're focusing on it in these early sections of the chapter. But as we move forward in the chapter, we're actually going to start solving more problems without even considering work, by just considering beginning states and final states. Okay, but you'll see that when it comes. And finally, type 4, fairly complex problems that involve work, constant non-zero acceleration, and forces at various angles, that is. Okay. So let's look at a type 1, example 1. You pull a heavy couch across the floor of a carpeted room. You pull parallel to the ground. The coefficient of static friction between the couch and the floor is μs equals 0.54, okay? Rough carpet. And the coefficient of kinetic friction is less, okay? I don't say how much it is. It's not necessary for the problem. The couch has a mass of 225 kilograms. So in part A, we're asked, if the couch is at rest and you pull on it with a force of 500 newtons, how much work have you done? Okay, so here's the free body diagram, pulling force, friction force. Okay, so well, how much is the friction force, by the way? Well, we take μs and multiply by Fn, which would be just so μs times gravity times mass. That's 1,190 newtons. Well, that means that the static friction force is actually greater than the pulling force. In that case, the couch isn't going to move. And if the couch doesn't move, then the work done by pulling has to be 0. Work is always 0 if displacement is 0. Okay? All right. So that's a good thing, right? Good reality check. You can't do work if things aren't moving. End of story. Now, this person could tire themselves out by pulling on the couch and having it not move because internally, their blood is doing work, their heart is doing work, their muscles are doing work, but the couch their external force on the couch is not doing work, okay? So that's why you might be like, you can tire yourself out even though, you're not doing any work externally because you're still doing work internally, okay? So part B, all right, part B, we're asked if the couch is already in motion, okay, so now we're definitely doing work, and you pull on it with a force of 500 newtons and the couch slides 4 meters at constant speed, so you're obviously much less kinetic friction coefficient than static friction coefficient. How much work have you done? Okay, now I don't ask for this, the coefficient of kinetic friction. You could actually solve for it here using our previous methods, but it's not relevant. Okay, and so then in this case, it's as simple as just taking 500 newtons, the pulling force, multiplying by the displacement we were given, and then multiplying by cosine of the angle between the two. And here I didn't mention the angle between the two because there is no such thing as a displacement vector, so it didn't make sense to have an angle. But here, clearly, we have a displacement which is in this direction. This would be our d vector. And so then the angle between F pull and d is 0. Well, cosine of 0 is positive 1. So that means our answer is just 500 times 4, or 2,000 joules. That's how much work the pulling force does. Okay, that's how much work the woman does on the couch. Okay, now, okay, part C. In both cases above, how much work has friction done? Okay, because every individual force does work. That's a good idea to wrap your head around and get used to. Okay, so the pulling force did a certain amount of work. It was positive because it was parallel. Well, the friction force is definitely the other way, so we should expect it to do negative work, right? Cosine 180 degrees is negative 1, okay? All right, but first, in the first case, in part A, there was no displacement, so friction likewise must have done 0 work. So we know for part A, 0 joules, no work, okay? For part B, however, it would be negative 2,000. And I know it would be negative 2,000 because I know that net work is 0 since the final velocity equals the initial velocity. And if net work is equal to 0 by the net work formula, net work is just going to be work of pull plus work of friction. This is just 0, so then we can just solve for work of friction, and it's just negative work of pull, or negative 2,000 joules. Okay? All right. So simple case, but good for kind of getting used to what we mean by work, right? Okay? Example 2. All right, we got a box. We're given its mass. Again, constant speed, so 0 acceleration. That's why it's a type 1 problem, right? Example 2. If the box is pushed a distance of 2.009 meters, right? Very accurate measurement here. And the pushing force is, the pushing force does 356.6 joules of work, then A, what is the magnitude of the pushing force? So here instead of solving for work, we're actually given work, we're going to solve for F, okay? And then in part B, what is the coefficient of kinetic friction between the ground and the box, okay? So let's take a look, right? Here's our picture, right? Just like the couch, there is a pushing force, right, moving parallel to the displacement vector, and there's a friction force moving anti-parallel to the displacement vector. Anti-parallel, by the way, means the opposite way, okay? All right, so part A, work of push, is F times D times cosine of 0. All right, so that means that F of push times D is just the work of push, okay, because the cosine of 0 is just 1. And then I can solve for F push, which would just be the work in joules I was given divided by the displacement I was given. And that tells me that my work of push is 177.5 newtons. All right, excellent. Okay, done. We found the pushing force based on the work that we were given and the displacement that we were given. Okay, and the angle, I suppose. Okay. All right, part B. All right, and the work friction has to equal the negative work of push. Why? Because the velocity is a constant. Thus, the net work is 0. See how that can be a really useful tool, right? That whole work kinetic energy theorem, really fast way to compare between forces. Okay, so that means that the work of friction equals the force of friction times displacement times cosine of 180, which then is equal to the negative the work of push. So I set it up this way so that the cosine of 180, which is just negative 1, cancels with the leading negative on the work of pushing value, which we already know to be, oh, there it is, 356.6 joules. Okay, and so then that's, so then when we realize then we're solving this equation, the negatives are gone, and we're just going to solve for mu k. All I've done is replace the force of friction with mu k Fn, and I've replaced Fn with mg because level ground. Okay, so that was kind of I could have set up a free body diagram to confirm that, but level ground, we should be, aware that friction force is always mu k mg for level ground. Okay, all right, and then there's our displacement because we're talking about work after all. And then I'm just going to solve for mu k, so it's going to be the work of pushing, all right, divided by mgd. All right, so there's our values, and we end up with 0.33210. So we're able to solve for the friction coefficient using a new method, not, no free body diagram really, just using this idea of the work kinetic energy theorem and the definition of work. Okay? All right, let's move right along. Okay, I got a quick concept question here. And this is a good reality check about the whole angle business. It's good to see a concrete example here, or at least concrete concept. A crate moves 10 meters to the right, we actually don't care about the values, on a horizontal surface as a woman pulls on it with a 10 Newton force. Rank the situations shown below according to the work done by her force least to greatest. Okay, well, let's think about it. There's the ranking. Done thinking. Why do I know the ranking right away? Well, because I know when it's perpendicular, it's going to be 0. Okay, so the work when it's perpendicular is 0. So I know that this one has to be the least. Okay, this force is going to do no displacement. Okay, because it's, because the box needs to slide side to side. So this one does not do work. Okay, that perpendicular force to the displacement vector means 0 work. Okay, this one is parallel. Parallel is max work. You can never do more work than having a force parallel to a displacement for a given force and displacement. Okay, so this has to be the biggest case, which means that this one has to be in between. And indeed, right, we can see the angle is in between. Okay, so there we go. 3, 2, 1. Okay, all right, looks good. All right, so example 3. You lift a box with a mass of 7.5 kilograms at constant speed, a vertical distance of 2.5 meters. So constant speed again, okay? How much work does your force of lifting do in the box during the lift? How much work does the force of gravity do in the box during the lift? What is the net work done on the box if we ignore drag? And then finally, part D, what is the final speed of the box if the net work is increased by 2 joules? Oh, okay, so part D is different, and part D is the reason that this is a type 2 problem, because otherwise it would just be a type 1 problem, because it's all, either parallel or anti-parallel, and up until part D, it was all constant velocity. But we got acceleration in part D, although we're not really thinking of it in acceleration. Instead, we're thinking of it in terms of change in kinetic energy, and we're going to use that to solve for the final velocity. Okay, so let's just run through this here. All right, so from net work equal to 0, since velocity is constant for part A, we know that the work of lifting must be equal to just mgd times cosine of 0 degrees, which then would just be equal to 184 joules. Okay, all right. For part B, the work of gravity just has to be equal to the negative of the work of lifting, again by the fact that net work is equal to 0, which means that the work done by gravity is just the opposite in sign of the work done by lifting, so it's negative 184 joules. Okay, and we're asked then what is the net work? Well, we already know it. We basically already assumed it, but you can just say, by definition, or by the fact that the final velocity equals the initial velocity, net work must be 0 joules. Okay, but let's change things for part D. Now we're going to have a non-zero net work. So now we're going to use the work kinetic energy theorem, but instead of just setting one side to 0, we're going to have one side actually have some terms here. Now the initial velocity is still going to be assumed to be 0, but now we're going to solve for V final. Okay, so I'm going to go ahead and set that up. As I solve for V final, just isolating on one side, I end up with 2 times net work over m inside the square root. So this is kind of a useful equation. This will come up quite a few times. All right, so plug in our values. All right, notice my net work is pretty small compared to my actual work. So I basically, in other words, my lifting force is just a little bit bigger than my gravitational force. It'd be 186, right? Which means, when I subtract 184, I have a difference of 2. So not that much, excess energy in a sense, but that excess energy is going to go to kinetic energy. It's going to go to the energy of motion, which means it's going to be manifested in a greater final velocity. All right, and we end up with 0.731 meters per second. Notice that this depends on mass, right? It does depend on, the inertia, depending on how much final velocity you get out of the system, okay? Depending on your excess work. Because that's what a net work greater than 0 is, essentially. It's excess work, and the excess work does something. It becomes acceleration, or it becomes an increase in kinetic energy, okay? All right, let's look at another one. A car is driving at 16 meters per second when its wheels stop turning and it slides to a stop from a constant friction force in 10.5 seconds. If the car has a mass of 821 kilograms, then A, how much work is done by friction, and B, what must be the friction coefficient between the wheel rubber and the road, okay? All right, here's the picture, right? And we have a non-zero initial velocity. We have a 0 final velocity, so we definitely have a change in kinetic energy, and we got only a single force acting, the force of friction, okay? Now that's interesting, right? So that almost makes this problem seem easier. In a sense it is, right? Because all our previous problems always had 2 forces, okay? This one really just has a single force, all right? But the thing is, when you just have a single force, you have to have a change in velocity, which means you have to have a change in kinetic energy, right? Now part A, though, has a really simple way of solving it, a real kind of powerful application of the work kinetic energy theorem. We just write F work net equals the work of friction, since it is the only force, thus the work done by that only force must be the only work, okay? And that means that the work of friction is just equal to negative 1/2 mv initial squared, okay? Why is it negative? Well, because remember, the work of friction is equal to 1/2 mv final squared minus 1/2 mv initial squared. Well, the v final was 0, so all that was left was that second negative term, okay? So then I just go ahead and write this out. So we got a work of friction equals negative 1/2 times mass, 821 kilograms, times initial velocity, 16 meters per second squared, okay? And so that tells me that the work of friction is negative 1.05 times 10 to the 5 joules, okay? So that's great, because then we see that the negative just comes naturally from the work kinetic energy theorem. Now the negative also comes from the fact that the work, the friction vector, the friction force vector, I should say, is anti-parallel to the displacement vector. So, but that, just because there's 2 things that arrive at the same point doesn't, confuse the matter. It just means that the definition of work is consistent with the work kinetic energy theorem. Here, we just arrived at the negative to the work kinetic energy theorem rather than through the definition of work, whereas all the previous times we always arrived at the negative to the cosine, right? Okay? All right, well, let's take a look at part B. I know I make a big deal about the negatives, but like I always say, people get negatives wrong. I get negatives wrong. You have to pay attention to them. They're so important, okay? Get your sign right. All right, so first thing we need to do to answer part B, because part B is asking for the friction coefficient, is we have to do a little bit of kinematics here. We have to actually find D, because we weren't given D, right? I kind of obfuscated the information here. I gave you the initial velocity and the final velocity, and I gave you the time it takes to stop, okay? So let's use that information. Let's find the acceleration based on the velocity and the time. So our acceleration is negative 1.52 meters per second squared. We're just going to use that for our next step in order to find D. And I could have kind of, combined equations and kind of come up with a new kinematic equation, but here I just decided to do it in 2 steps instead, and we find that our D is 84 meters. Okay, that's the magnitude of our displacement vector. Now we can just go back to the definition of work. So the work of friction is the force of friction times D times cosine of 180. There's that negative, all right? And that's super important, because look, then when we plug it in, right, we're going to have, so we have the negative on that side. I'm going to multiply both sides by negative 1. So now I end up with negative the work of friction, mu k mgd. Well, when I plug in the work of friction, I'm going to plug it in as a negative, because it is a negative value, which means the negatives are going to cancel out, which is good, because we can't come up with a friction coefficient that's negative. That doesn't make sense. All right, so this is what, this is why the sign matters. Okay, I know I'm like a broken record, right? Okay. And so then we kind of isolate our friction coefficient, work of friction divided by mass, gravity times displacement. All right. plug in our values, okay? So here I plugged in my value, the negative, okay, which means it canceled because I had a negative of a negative, so they canceled out, all right? Which means I'm just left with positive 1.05 times 10 to the 5 joules, or 105,000 joules in the numerator. And then we got the mass, the gravity, and the displacement down in the denominator. And there we go. We get a friction coefficient, a kinetic friction coefficient of 0.155. Okay, all right, let's continue on with some more complicated examples. Okay, and continuing with the next example, example 5, we have a force that's being applied to an object, but now the force is not parallel to the displacement. Notice that there's an angle that the force is at. This problem is set up to highlight the fact that we're only going to be looking at this component, the F cosine theta component for this particular angle theta, in order for work to actually be done. All right, so let's take a look. So we have a certain unknown mass. We know that angle theta. We know the pushing distance as well, right, in order to calculate work. So let's look at the first question. If the force is applied continuously along that distance of 1.9 meters, how much work has the pushing force done? Okay, so we'll simply take a look at the definition of work here. F push times displacement times cosine of the angle between the two. In this case, that's theta. And that just ends up being the following, or 1.91 Newton meters. Okay, I could have written joules, but I mixed it up and used the units of Newton meters. Okay, totally valid. Okay, now in part B, what is the net work? Okay, let's take a look. All right, so we're gonna look, and we have here, let's see, we're told, which causes the block to accelerate from rest. Okay, so the net work is the pushing work plus if you think of all the forces that can do work here, the work done by pushing, the work done by the normal force, the work done by gravity. Those are it. Okay, but well, let's think about it. Right, we got a bunch that are 90 degrees. In other words, between the normal force and D, that's 90 degrees. Between mg and D is also 90 degrees. So how much work are these two forces going to do? None, zero. All right, so that means the only work being done is the work of the pushing force. That means the net work is 1.91 Newton meters. Okay, so in part C, how fast is the block going, or how fast will it be going at the end of 1.9 meters? Okay, and remember, it did start from rest. Okay, all right, well, let's look. Okay, so we're just going to use the work energy theorem, which means that the net work is just 1/2 mv final squared because, well, its v initial was 0. And we'll go ahead and solve for v final, just the square root of 2 times net work over m. I told you that we'd see that formula again. All right, plug in our numbers, and we get 1 meter per second. Nice round value. Okay, so the idea there is we have acceleration, and we also have a component of force that does work. And so in addition to these two forces doing no work, likewise, this component of the pushing force does no work, right? Because that's the component of the pushing force that's perpendicular to the displacement. Okay? All right, so here's basically the same problem again, but we've added friction. All right, so how is that going to change things? Okay, so the idea here is we have, this one is a different type of problem because I think this one might be constant velocity here. All right, yep, constant velocity. Okay, so let's take a look. Okay, so let's consider our sum of forces, okay, because that's going to be relevant because especially we're going to have to consider what the friction force looks like. Namely, the friction force is going to get affected by the vertical component of the pushing force, because this component, that downward component of the pushing force, makes the normal force larger, thus makes the friction force larger in magnitude. Okay, so we have to consider that, and this is just a good reminder of where to look for that information in the sum of forces. They're both going to be equal to 0 because unlike the previous problem, this problem has no acceleration. Okay, so here we have our net work. All right, so it's going to be pushing force plus the work done by friction. It's 0 here, all right, again, because no acceleration, thus no change in velocity, thus no change in kinetic energy. So net work is equal to 0. That means that the work done by friction is just equal to the negative of the work done by the pushing force. All right, so then the work done by friction is the force of friction times displacement times cosine of the angle between the two. All right, it's called phi here. All right, and then I'm just going to replace the normal force with the expression that I get from my sum of forces in the y direction, f sine theta plus mg. All right, and what is the angle between the friction force and the displacement? It's 180 degrees. That's why I call it phi and not theta, because it's not theta, right? Because in other words, this is 180 degrees. Okay? All right, so that's, of course, just going to become -1. All right, so the -1 from the cosine of 180 comes out in front. All right, and then I'm going to set that equal to the negative of the work done by the pushing force. All right, which I know to be 1.91 Newton meters. How do I know that? Well, because it's the same pushing force and the same D. All right, So it has to be the same 1.91 meters. That hasn't changed. And it's the same theta, by the way, right? And since the work of friction is equal to the negative, then the negatives cancel out based on this equation right here. Okay, so again, we have a negative that comes from the cosine of 180, and we have a negative that comes from the work, or the net work equation, basically the work kinetic energy theorem. All right, so then that's going to allow us to solve for the friction coefficient, mu k. And this whole solving for mu k and having it not be negative by canceling the negatives out, we saw that in a previous example, right? So kind of compare, because the procedure is very similar. Okay, so then we just plug in all our numbers and solve for mu k, and we get 0.026. So actually a very small friction coefficient, but definitely still realistic. Part B, how much work does the friction do on the block? Okay, well, you can just plug things in now. All right. Well, because work net equals 0, we know that it's just negative 1.91, right? That was kind of implied, right? We could have done that up here, right? So sure, it's a part B, but it's kind of a very easy part B because essentially we already know that information. But do remember that it is negative. It's negative because of the work energy theorem, and it's negative because of the cosine of 180, right? Depending on how you think about it. All right, so there we got another good example. All right, so I have two more to show you. All right, so this one we have forces at angles, and in this one we actually also have an acceleration. Okay, so let's take a look. No, never mind. This one is constant velocity. That's why it's this type, the type that's purple. Okay, constant sliding velocity. Yep, that's key. Okay. So what's going on? So this one obviously is a little bit different. Before it was just the pushing force that was at an angle. Now, there's kind of a different angle between the gravitational force. It's this whole tilted coordinate system. How are we going to tackle it? Okay. Well, we're just going to go with the definition of work, right? We'll find that it's a powerful way to approach a problem like this. All right. So what I mean by that is, let's think about this. Okay. So first of all, what were we asked for initially? In part A, we're just asked how much work has gravity done during the slide. The slide, it has a length that we know. We know the angle of the driveway in this case. We know the mass of the cardboard box with child inside, because that's what's happening here. It's a kid sliding down the driveway in a cardboard box, okay? And so we just need to find out how much work is done by gravity, okay? Well, let's think about it. Well, we got the force of gravity. We've got L, which we know, and we got cosine of phi, right? So I put phi right there, all right? And phi is 90 minus theta, okay? It's not equal to theta. Theta would be this angle right here. That would be theta. So we can clearly see that phi is just the complement of theta, okay? So then we can just plug in our values here, right? We got the 33 kilograms times gravity. That's our gravitational force. Then we've got our distance, and then we got cosine of our angle. All right, so there we go. That is the work done by gravity, 628 joules, okay? And so we could have also found that 628 joules by just taking mg and multiplying it by this distance, basically this component of L, right? It's kind of like Ly. So that's the same idea. It's the same trigonometry, just instead of taking a component of the force, effectively, it's kind of what I'm thinking of doing here. Instead, it would be taking a component of L. Either way, it's the same effect. Okay, but there is your work done by gravity. All right. So in part B, we're asked how much work does friction do? Well, since velocity is constant, net work is equal to 0 joules, therefore friction has to do negative 628 joules, because there's no other force acting here that's doing any work, right? Because we think about it, that the normal force is here, but the normal force is completely perpendicular to the displacement L, therefore the normal force cannot do work, right? A component of gravity can, and certainly friction can, okay? All right, and then finally, what is the friction coefficient between the box and the driveway? All right, so kind of question I asked quite a bit here, all right? And so then we're just going to set this up. So from the fact that the work done by friction is the friction force times L times cosine of phi, and phi here is not the same phi, okay? But it's the phi that's relative to the friction force, okay? So it would be this phi here, okay? Okay, and I clearly show then that the phi is regarding the friction force is 180. I get, excuse me again. I guess I could have called it a different letter, like beta or something, but I use the same letter for it. All right, but we can quickly see that it is 180 degrees. Cosine of 180 is negative 1. All right, so then we just solve. We're going to use that Fn is mg cosine theta. I don't do a full free body diagram to show that. We're kind of maybe used to already seeing that. Basically, it would be this component of gravitational force that's equal to the normal force. If we did the sum of forces in y, if y was measured like this. Okay, so anyway, that's the normal force. Plug it all in, solve for the friction coefficient, the kinetic friction coefficient, and there we go. Okay, and well, there's our value in the next step, 0.333. All right, So that's it. Okay, so you can see definitely, there's these new ideas with the work kinetic energy theorem and the definition of work, but then, ultimately we are still using some sum of forces in order to fill in missing information. And that's the same for example 8, which is kind of just putting all the ideas together. All right, so let me kind of read this one through because there's a lot going on. So if a person pushes on a 365 kilogram piano at an angle of 14 degrees above a 24-degree incline, okay, so we got two separate angles there, and the friction coefficient is 0.38, and that's the kinetic friction coefficient. The piano will accelerate down the incline, all right, so the person isn't pushing enough to stop it from accelerating, but it would accelerate less than if they weren't pushing. After sliding for 2.5 meters, how much work is done on the piano, by the man, by friction, by gravity? And what is the net work done on the piano? What is the final velocity of the piano if it started from rest? Okay, so this one's interesting because this one definitely does not have a zero net work. Okay, so that means that inherently it's a bit more complex because we can't just, kind of quickly solve for things by saying, oh, well, look, network's equal to 0, and then just, it's easy when you have one side of the equation equal to 0, right? But here we don't, and we don't know acceleration immediately, right? So how do we do this problem? Well, first of all, we draw all the angles, okay? Obviously a lot going on, right? Normal force perpendicular to the surface. The pushing force is some angle phi above the angle of the ramp. The angle of the ramp is theta, all right? Then I also have the angle of the gravitational force, which would have its components. That's also theta because that matches the tilt, okay? The friction force is parallel to, I call it the ramp, but I will call it the incline. Displacement is also parallel to the incline. Here is our coordinate axis, a tilted coordinate axis. We have an angle here called phi p. That is the angle between D and FP, so hence the name phi p. And then the final angle we have is phi g. Phi g is the angle between the gravitational force and the displacement, okay? So those are the angles we care about, namely phi g and phi p, because those are the ones that are actually going to show up in the definition of work. These other angles are more for like the free body diagrams, okay? Including that phi. So there's three separate phis. Phi without a subscript, then phi p, phi g, and then one theta, okay? All right, but here I'll label them, all right? So we've got, so phi p is just 180 minus 14, okay? We can see that in the figure. Phi f, which actually I don't even show in the figure, but it would be this one right here. That's just 180 degrees, okay? Phi g is 90 minus 24. That's this one again, okay? All right. Theta is 24 degrees, okay? Oh, and also phi is 14 degrees, okay? Lots of angles, but take pause if you need to keep all the angles straight, but they're all clearly shown here, Okay. All right, zoom out a tad. All right, so then I have my free body diagram. So here's just the magnitude of the pushing force, okay? Let's see, so, well, I guess I left that information out. That's why I had to add it here. Sorry for that. I forgot that in the solution, person pushes on a piano. Yeah, I was supposed to say how much they push with. That's supposed to be in the body of the problem. So that is information that it was given. So it's stated there. Okay, but then carrying on, we're going to write our sum of forces. So we got our sum of forces in x, and that's with the tilted coordinate system, and there is acceleration in the x direction, and there's a sum of forces in y. And we could find, we have the displacement, so we could find the final velocity entirely with solving for a and then doing kinematics along the actual incline. So we could definitely answer part E without considering work at all. But since parts A, B, and C, we were explicitly asked for work in units of joules, we have to use the definition of work. And that's really what this problem is all about. It's just using the definition of work a few times. All right? So let me show you what that looks like. Okay? So this, continuing with the free body diagram, I want to express the friction force. So the friction force by definition is mu k Fn. Okay, well in this case Fn is Fgy minus Fpy, all right, because we're effectively making the piano a little bit lighter because the person's pushing up on it a tad. And so then it ends up being a component of gravity, the mg cosine theta component, minus the y component of the pushing force. So minus Fp sine phi, okay, and this is the original phi, the 14 degrees, not the phi of any of the subscripts. Okay, so that is our normal force right there in parentheses, and then by definition the friction force is mu k times that. Okay, and then that means that the work done by the normal force is, well, actually kind of a side note, the work done by the normal force, which we weren't asked for, is just going to be 0. Why do we know it's 0? Because it's cosine of 90 degrees. Okay, and that 90 degrees is not shown in the figure. That's just the right angle. That would be the right angle between the normal force and the pushing. So that right angle right there, between this vector and this vector. Okay, so right away normal force is 0. Okay, I just wanted to be thorough, I guess. All right, so let's see. In part, looks like I'm answering part B first. This is one of my older solutions, right? This is why it's got some oddities to it. So part B, how much work is done by friction, okay? So we've got the mu k, okay? We've got, so this whole business here is just the magnitude of the pushing of, the friction force. This is d, which we know, and then this is cosine of the angle between those two vectors. So in other words, it's cosine of the angle between this vector and that vector. Well, what is that? That's just 180, okay? So then the work done by the friction force is 2,770 joules, okay? And that one, let's see, because it seems like it should definitely, yeah, there should definitely be a negative on that one. So that one should pick up a negative. Looks like I left it off, okay? And then the work done by the pushing force, that one does correctly have the negative, all right? Because that's just going to be the value of 1440 times the displacement times cosine of phi p, and phi p we know is just 180 minus 14, and that's this angle right here, okay? And you can see why it's 180 minus 14, right? Because it's just the 14 is just that smaller angle right there, okay? And so that ends up being negative 3,350, okay? And again, this one should have a negative, all right? And then for gravity, all right, well, the work done by gravity is going to be positive, okay? And it's going to be, and we're going to use this angle here, the 90 minus 24, all right? That's our phi sub g. D is the same. mg is pretty straightforward, okay? All right, so then the net work is going to, when we sum those up, and let's see, so we're going to have 3,000, let's see, because we have a positive one here. It should be a negative net work. I guess I'll have to fix these values. I'll go ahead and fix it and re-upload with the fixed values. Okay, so check that out when I re-upload it, because again, this one should be negative, so that's going to change our sum a bit. And then we can just go ahead and solve for our final velocity. And then our final velocity is going to be in the positive x direction, but it's so it's going to be 4.09, and that may change when I correct my net work here. Okay, so the ideas are all valid. There's just there was a lack of a negative there. I didn't catch it when I was copying and pasting this in, but I'll fix it up. Take a look at the final solution, but do notice kind of how all the angles are complicated here, sure, but look how we can just kind of take each one individually into account using the definition of work. That's really the takeaway of a problem like this. There really wasn't any complicated algebra, was there? We didn't have multiple equations with multiple unknowns and have to do substitutions or any any tricks with subtracting one equation from another, like with the free body diagram problems. No, we just had to just calculate work, right, and make sure that we drew a picture where we knew the relationship between angles. That was so it's definitely a different approach from say a different force problem. Okay, all right. So that is it for lecture 12. Thank you so much for watching it, and stay tuned for the rest of the lectures from chapter 5.